Yeah, children. So, coming to magnetism, small revision about magnetism. Okay, so okay, children. In magnetism, first we'll study about the magnetic field. What is magnetic field, children? It is represented by B, children. Okay, what is magnetic field? It is the space around magnet. It is a space around magnet in which its influence can be felt. Its influence can be felt. Space around the magnet in which its influence can be felt. It is denoted by or it is denoted. Its units are Oersted. Okay, children. Space around the magnet in which its influence can be felt. What is the magnetic field, children? Space around the magnet in which its influence can be felt. The units are Oersted, and magnetic field consists of what? Lines of force. Magnetic field consists of what, children? Lines of force. What is line of force? Line of force is line along which line along which freely suspended magnet line along which freely suspended magnet line along which freely suspended north pole, children. Line along which freely suspended north pole tends means tries to move. Line along which freely suspended north pole tries to move. Okay, children, if you draw a line of force, how it will be, children? You will take compass, and wherever it is showing the arrow, compass will be like this. Arrow represents north. Wherever it shows north direction, we'll keep first dots, children, and we'll join them. Wherever it shows like this, we'll join them. Like this, we'll join them. Like this, we'll join them. Okay, so it will be somewhat like this, children. Okay, what are the properties of lines of force? What are the properties of lines of force? What are the properties, children? Outside they move from north to south. Outside they move from north to south. And inside they move from south to north. Inside they move from south to north. Okay, children? And if you see inside they are moving from south to north, and they are closed and curved lines. They are closed and curved lines. And if you see at poles, they are crowded at poles. Why they are crowded at poles? Because poles are stronger. They are crowded at poles. And no two lines will ever intersect. No two lines will ever intersect. No two lines will ever intersect. Why? If they intersect, field is in two directions. If they intersect, field is in two directions. If they intersect, field is in two directions, which is not possible. If they intersect, no two lines will ever intersect like this, children. If they intersect, field is in two directions, which is not possible. And tangent, if you draw tangent, if you draw tangent, if you draw tangent on line of force, tangent on line of force gives direction of magnetic field. Tangent on line of force gives direction of magnetic field. Tangent on line of force gives direction of magnetic field. So these are the properties, children. Properties are very, very important. They are asking it regularly, especially the fifth property. No two lines, why they won't intersect, they are asking. Why they won't intersect, children? Because two lines of force, if they intersect, it indicates field is in two directions, which is not possible, children. Two lines of force will never intersect. Two lines of force will never intersect. Okay, and what are the properties of lines of force, children? They move from north to south, outside, south to north, inside, and they are closed and curved. They are crowded at poles, and no two lines will ever intersect. And if you draw tangent, a tangent on line of force indicates direction of magnetic field. If you draw tangent any point on line of force, it indicates direction of magnetic field. Any point on line of force. Okay, children? So, magnetic field is space around the magnet in which its influence can be felt. Line of force is line along which a freely suspended north pole tends to move. Okay, children, these are the properties of lines of force. Now, children, around a current carrying conductor. Okay, suppose this is a current carrying conductor. Around a current carrying conductor, compulsory magnetic field is present. Around a current carrying conductor, magnetic field is present. How? In the form of concentric circles. How? In the form of concentric circles. So, if it is a straight conductor, magnetic field is circular. If it is a straight conductor, magnetic field is circular, and the magnetic field is directly proportional to current. More current, more magnetic field, and inversely proportional to radius. As you go away from the center, magnetic field decreases. If it is a straight conductor, magnetic field is circular. If it is a straight conductor, magnetic field is circular. And if ever it is circular conductor, magnetic field will be straight. If ever it is circular conductor, magnetic field will be straight. If ever it is circular conductor, okay, for circular conductor, magnetic field is straight. For circular conductor, magnetic field is straight. Here also magnetic field is directly proportional current and inversely proportional to radius. Okay. More current you send, more magnetic field will be there. Less current you send, less magnetic field. And as you go away from the magnetic field, strength decreases. Okay, children? Next one. I'll tell rules also, don't worry. Solenoid. Next, what is solenoid? What is solenoid, children? This is circular turns of copper wire wrapped in the shape of cylinder. Okay, it's a circular turns of copper wire wrapped in the shape of cylinder. If you keep any object with this, and if you pass current, it behaves as a magnet. It behaves as a magnet. Circular turns of copper wire wrapped in the shape of cylinder. Circular types turns of copper wire wrapped in the shape of cylinder, and in which, if you keep any object, it will become a magnet, especially if you keep steel. Steel will become permanent magnet, or else if you keep soft iron will become temporary magnet. Soft iron will be, but it behaves as a magnet with creating north and south pole and even lines of force. Inside solenoid, magnetic field is uniform. Inside solenoid, magnetic field is uniform. Inside solenoid, magnetic field is uniform. Uniform magnetic field is represented by parallel lines of force. Uniform magnetic field is represented by parallel lines of force. Okay. If you put steel, you'll get a permanent magnet. If you put a soft iron, you'll get a temporary magnet. Temporary magnets are called electromagnets. Temporary magnets are electromagnet. What is an electromagnet? Okay, substance which behaves as a magnet. Substance which behaves as a magnet only when current is passed. Substance which behaves as magnet only when current is passed. Substance which behaves as a magnet only when current is passed is called electromagnet. Okay, children, what are the advantages of electromagnet over permanent magnet? Electromagnet strength we can increase or decrease. Electromagnet strength we can increase or decrease. Whereas permanent magnet, once you get magnetism, you cannot increase. Electromagnets which are behaving temporarily, we can increase or decrease. How? Send more current, it will become strong magnet. Send less current, it will become weak magnet. Strength of the current, strength of the magnet we can increase, and even we can change polarity. Whenever you want, you can change north to south and south to north. Where it is used, they are used in bells, cranes, electrical appliances. Electromagnets are used. What is an electromagnet? Substance which behaves as a magnet only when current is passed. What are the advantages? We can increase the strength of the current or decrease. We can change the polarity. And where it is used, bells, alarms, electric appliances. So this is about solenoid, children. So on what factor the strength of the magnet inside the solenoid depends, means circular turns, number of turns, how many turns you keep, that was stronger it become, and current, children, okay, and the current and area of the circular coil, okay. So next one, children, this is solenoid. Next, okay. Next, whenever a current carrying conductor is kept in magnetic field, whenever a current carrying conductor is kept in magnetic field. See, children, this is current carrying conductor is kept in magnetic field. It experiences force. A current carrying conductor, when kept in magnetic field, it experiences force. A current carrying conductor, when kept in magnetic field, not to south, horseshoe magnet, children, if you keep, it experiences force. Okay, and the force experienced by current carrying conductor is directly proportional to force experienced by current carrying conductor is directly proportional to strength of the magnet. Take more strong magnet, more force. Send more current, more force. It will, okay. And take more length, more force. And if you keep perpendicular, when will be the force experience in maximum? Means if sin theta is 90 degrees, means you have to keep this. This is magnetic field. You can't see that. Okay, exactly 90 degrees you keep, children. If you keep perpendicular to the magnetic field, then that force will be maximum. When will be the force maximum? It's when you keep conductor perpendicular to the magnetic field. Force experienced by current carrying conductor is when you keep any current carrying conductor, when you keep any current carrying conductor in magnetic field, it experiences force. This principle is used in electric motors. This principle is used in electric motor. How electric motor is made? definition. What is electric motor? Which converts electrical energy. If you switch on, fan will burn no chill. So if electric motor is that which converts electrical to mechanical energy. What is electrical motor definition? It converts electrical energy to mechanical energy. Okay, and this is definition. And what is the principle, children? What is the principle of motor? It converts if current carrying conductor when kept in magnetic field, it experiences force. Current carrying conductor when kept in magnetic field, it experiences force. Okay, and how it is made, children? So simple, children. How it is made? You will take a strong horseshoe magnet. You will take a strong horseshoe magnet, children, and here you will keep an armature. Armature means in which circular tubs of copper wire is kept. This is an armature. Okay, so here split rings will be there, children. Here split rings will be there, and these split rings are attached to the brushes. The split rings are attached to the brushes, and then circuit. You switch on the current, children. When you switch on the current is flowing in magnetic field. When you switch on the current is flowing in magnetic field. Current is flowing, current is going like this in magnetic field. So it experiences force and it starts rotating, children. Because it experiences force, it starts rotating, and you connect it to the axle. To the axle you attach wheel also rotates. This is how instrument is electric motor is working. How electric motor works, children? How electric motor? The armature is kept in magnetic field. When you pass the current in armature, it starts rotating. What is the function of split rings? Split rings helps in changing the polarity. What is the function of split rings? Split rings helps in changing the polarity. What is the function of split rings and brushes? Brushes helps in conduction of current. Split rings helps in changing the polarity. Brushes helps in conduction of current. Split rings helps in changing the polarity. Armature is kept in magnetic field, and you pass the current. When current carrying conductor, armature is conductor kept in magnetic field, it experiences force, and this armature rotates, axle rotates, and wheel rotates. This is electric motor, children. This is electric motor. And to know the direction of force, here we will use Fleming's left hand rule. To know the direction of force, here we will use Fleming's left hand rule. What is Fleming's left hand rule, children? When three fingers of left hand, compulsory you should take left hand, not right hand, children. Left hand. When three fingers of left hand are stretched in mutually perpendicular directions, when three fingers of left hand are stretched in perpendicular directions, center finger gives the direction of wheel, forefinger gives the direction of children. Center finger correct, children, sorry. Remember like this: father, mother, child. Father, mother, child. Force, magnetic field, current. Father, force, magnetic field, mother, current. When three fingers of left hand are stretched in mutually perpendicular directions, then center finger gives the direction of current, forefinger or index finger gives the direction of field, and thumb gives the direction of force. Okay, children, father, mother, child, like that you remember, children. This is electric motor. And what is electric generator? Same thing, children. In electric generator, we will rotate the axle. In electric generator, we will rotate the axle. When you rotate the axle, this will rotate. Armature will rotate. When armature is rotating, children, what happens? When armature is rotating, see, children, how do you rotate the axle? By putting petrol or kerosene or diesel, we will rotate the axle. When axle is rotated, armature rotates. When armature is rotated in magnetic field, it produces current. And if you put any bulb or anything, it flows. Opposite, children. If you pass current, it is rotating. Okay? If you rotate, you will get the current. If you pass current, it is rotating in motor. In generator, if you rotate this, you will get the current. Okay? Now, what is generator definition? What is generator definition? Children, generator is defined as electrical generator. It is defined as it converts mechanical energy to electrical energy. Means if you rotate, it produces current. If you rotate, it produces current. And what is the principle? What is the principle, children? Okay, relative motion between coil and magnet. Relative motion. Relative motion means anyone should rotate. Relative motion between coil and magnet. Relative motion between coil and magnet produces current. Relative motion between coil and magnet produces current. How? By electromagnetic induction. Relative motion, anyone should rotate, children. Relative motion, either you should rotate this or this. Relative motion between coil and magnet produces current by electromagnetic induction. Okay, well, that is principle. And what is the definition I told, and diagram I told. And here, what is produced? Current is produced. How to know the direction of current? Okay, correct. Direction of current is known by Fleming's right hand rule, children. Fleming's right hand rule. What is Fleming's right hand rule? Same definition, children, but here right hand will stretch. When three fingers of right hand are stretched in mutually perpendicular directions, then central finger gives the direction of current, and forefinger gives the direction of magnetic field, and thumb gives the motion of the conductor. In this direction, it is moving. Thumb gives the motion of the conductor. There, in motor, thumb gives force. Here, thumb gives motion of the conductor. Okay, children, this is generator. So, generator of two types, children: AC generator and DC generator. What current it is producing, it depends upon AC or DC. AC generator and DC. AC generator produces alternating current. DC generator produces direct current. Alternating current means polarity keeps changing, children. Polarity changes. Alternating like this, polarity keeps changing. Whereas direct current, polarity does not change, children. Polarity does not change. In direct current, polarity does not change. In direct current, polarity does not change. Okay. In AC current, children, if you see in alternating current, we can send it long distances. We can send it long distances without energy loss. Here we cannot send. We cannot send, children. Wherever it is produced, they choose. AC sources, if you see, hydel power stations and thermal power stations. And what are the DC sources? Cell or battery. Cell or battery. Where battery is kept, there only we should use. We can't keep wire and we will use somewhere for the battery. Okay, these are the differences. Main difference between AC and DC, it can send it long distances, we cannot send. And here we will use full rings, children, and here we will use half rings or split rings. These are the differences between AC and DC. Okay, and you also know what is an earth wire. Children, there are three types of wire are there: live wire, neutral wire, earth wire. Live wire is red in color. Neutral wire is brown or blue or black, anything yellow. Earth wire is compulsory green, children. What is an earth wire? Earth wire is maintained at 0 volt potential. Earth wire is maintained at 0 volt potential. Okay, earth wire is maintained at 0 volt potential, connected to earth. It is connected to earth. Its symbol is like this somewhat, children. Earth wire symbol is like this. Okay, it is connected to earth. Okay, and it creates low resistance path. Earth wire creates low resistance path. Earth wire creates low resistance path. All excess current flows into earth. All excess current flows into earth. All excess current flows into earth. Where it is connected? Connected to metallic case of instrument. It is connected to metallic case of instrument. And what for it is connected, so that user will not get severe electric shock. User will not get severe electric shock. This is earthware, very important 3 marks question they are asking. Earthware is maintained at 0 volt potential, connected to earth, and it is connected to metallic box. And children, all the excess current, because it is creating low resistance part, all the excess current flows into earth, and user will not get any shock, children. Live wire carries the current, children. In India, we are carrying 220. We will send it to the home 220 volts. Okay, and 50 hertz current frequency. 50 hertz frequency. And neutral wire, what it will do, children? What is the function of neutral wire? Neutral wire maintains constant potential difference with the live wire of 220 volts. Neutral wire maintains constant potential difference of 220 volts with the live wire, children. Okay, these are the connections. And children, I told you, around the current carrying connector, magnetic field is present. Around the current carrying connector, magnetic field is present. To know the direction of magnetic field, we use which rule, children? Right hand thumb rule. Right hand thumb rule. To know the direction of magnetic field around a straight current carrying conductor, we will use right hand rule. To know the direction of magnetic field, we use it. When three fingers of right hand are stretched in mutually perpendicular directions, thumb in the direction of current, then the cutting of fingers gives direction of magnetic field. Thumb should be in the direction of current. Thumb in direction of current. Thumb in direction of current. Then curling of fingers gives direction of magnetic field. Thumb should be in the direction of current. Down is down. Up means up. Like this, like this. And the curling of fingers gives direction of magnetic field. This is right hand thumb rule. What for right hand thumb rule is used? To know the direction of magnetic field. What for right hand thumb rule is used? To know the direction of magnetic field. What for Fleming's left hand rule is used? To know the direction of force. What for Fleming's right hand rule is used? To know Fleming's right hand rule is, you know, the direction of current. If you know direction of magnetic field, you have to use right hand thumb rule. Fleming's left hand rule is for force, right hand rule is for current, left hand rule is for force, right hand rule is for current. Direction of magnetic field is B. And if you want to know the direction of deflection of compass, If you want to know the direction of deflection of compass, then we have to use more swimming rule. If you want to know the direction of deflection of compass kept near current, means here current carrying conductor is present, children. Okay, here you will keep compass. In which direction it will deflect, left or right? To know that, we have to use swimming rule. In swimming rule, what does it state? Imagine a person swimming in the direction of current. Imagine a person swimming in the direction of current. Then curling of figures gives direction of magnetic field. Sorry, children. Imagine a person swimming in the direction of current. Then north pole of this compass deflects towards his left hand. Imagine you are swimming in the direction of current. Imagine you are swimming in the direction of current. Imagine you are swimming in the direction of current. Okay, children? Imagine you are swimming in the direction of current. Then compass needle deflects towards his left hand. Compass needle deflects towards his left hand. Imagine you are swimming in the direction of current. Compass needle deflects towards his left hand. Children, are you able to hear? Can you please confirm?
Yes, sir.
Yes, sir.
Yeah, children, this is about the magnetic field, children. All rules I told and all the topics I told. Anyone have any doubt, you can ask me.